Jack has worked on distance regular graphs and related topics for many years, going back to his PhD in 1994 from the University of Eindhoven, Eindhoven University of Technology. And his advisor was Andreas Brouwer. In his lectures this week, Jack's going to speak on a characterization, Q-polynomial distance regular graphs, or maybe he's changed the title, a mini course on distance regular graphs. Okay, one way or another. Jack, please.
Thank you so much, Paul. I'm sorry I cannot be there. There are too many restrictions in this country. So therefore I have to do it online. I also apologize that there are probably many misprints in my file. I'm sorry for that already. So knowing myself. Secondly, the course is about characterization of distance regular graphs. It will be a very different course than Paul will give later today. I will look at more the geometric methods and using his tools developed by Bose, Terwilliger, and others. I will use them and then we will see how far we come this week. Okay, let's get started. So I will talk today. I will talk about distance regular graphs. I will give the definitions and examples. We'll talk about Bannai's problem, and then as a second part, I will characterize the Hamming graphs and the Johnson graphs. So let's start then. Okay. This is first to have the notation that everybody is with me. My graphs are undirected and simple, no loops and no multiple edges. And if the graph is connected, that means for any two distinct vertices, the existing part connect them. Then we can define the following notions: the distance between two vertices x or y, the length of a shortest part connecting them. So the diameter of gamma, that is, if I have a graph gamma, that is the maximum distance occurring in the graph. That means if I take all the pairs and I look at the distance of all the pairs and I maximize that, that is the diameter. And for me, gamma I of x will be the vertex distance I from a vertex x. Gamma x of x is the gamma 1 of x, are the neighbors of x. I of x is the order of gamma I of x, and kx is the valency of x, is k1 of x. And the subgraph induced on gamma x is called the local graph of gamma at x. All the subgraphs I will use in this course are induced subgraphs. If I forget to mention that, I will always mean induced subgraphs. So now a connected graph gamma is called distance regular, or DRC. I usually write DRC instead of distance regular. If there are numbers AI, BI, CI, and they are between 0 and the diameter. So for any two vertices with distance I, we have that the vertices at shorter distance from the neighbors from y at shorter distance from x, that number is Ci. The number of vertices at distance I, the number of neighbors of y at distance I from x, that is gamma I, that's AI. And the vertices at distance I plus 1, that is BI. And of course, BD is 0 and C0 is 0. Note also that C1 is always 1. And clearly, we usually write K for B0. So instead of B0, we usually write K. And instead of C1, we write C1. And we look at the intersection array because as BI plus CI plus AI is K. If you know the BI and the CI, then you know the AI. So I already said that C1 is always 1. I will look at examples. First, I will look at the Hamming graphs. So now I take two integers Q and N, Q at least 2 and N at least 1. and let Q be the alphabet 1 to Q. And the Hamming graph, some people prefer 0 to Q minus 1, but Hamming graph H and H and Q has vertex set Qn, Q to the power n. That means the vectors of length n with entries in Q, and two of such vectors are adjacent if they differ in exactly one position. And it's not difficult to see the diameter equals to n. The n2, hn2 is just the n cube. They are distance regular with ci equal to is I. And this graph gives an algebraic framework to study codes, especially bounds on codes. For example, the Darcel linear programming bound is one example, and the Schrijver bound who uses Terwilliger algebra is another. So then I will talk about Johnson graphs, and that is you take two integers n and t between at least t at most n and t at least 1. Then the Johnson graph j and t has vertexes the t subsets of n. I denote it by this symbol. And two of such sets are adjacent if they intersect maximally. That means if the intersection of A and B is t minus 1. It's not difficult to see that J and T is isomorphic to J and n minus T, and the diameter is the minimum of these two numbers, T and n minus T. We usually take n at least 2T. And it's a distance regular graph with Ci is I squared. And this is a way, a framework to study these signs, especially 2D signs or 3D signs and so on. So now I will look at distance transitive graphs. Distance regular graphs were introduced by Norman Biggs in the late 1960s as a combinatoric generalization of distance transitive graphs. Okay, which we now will introduce. So we take a graph gamma and a bijection from the vertex set to itself is an automorphism of gamma if edges go to edges. So if xy is an edge, even of because all our graphs are finite, so we only need one implication. So if xy is, because it's the bijection, if xy, okay, implies that phi of x, phi of y is also an edge. So an edge goes to an edge and non-edge goes to. I'm sorry for the problems. So we will look at I was telling you that distance regular were introduced as a combinatoric generalization of distance transitive graphs, and that is what I will introduce that. Somehow there's also distance regular graph via the association scheme, the P-polynomial association schemes, and that you have to listen to Terwilliger's talk to understand what that means. So I will do the distance transitive graphs. So I will look at a graph, and then I look at automorphism is a bijection of v to v, so that if xy is an edge, then the image is also an edge. And in connected graph is distance transitive if for any vertices xy, y, x, y, u, v, so that the distance between x and y is equal to the distance between u and v, there exists an automorphism, so that the image of x is u and the image of y is v. Note that the distance transitive graph is always distance regular and hence regular, because that means that if I look at the vertex, the point stabilizer of vertex, that point stabilizer is transitive on the gamma I of x. That makes it distance regular. Any of the distance regular graphs are distance transitive, but for example, any quadratic form graph of diameter at least 2 is not distance. All known infinite families unbound diameter of distance transitive graphs comes from classical objects, or I should have said the distance regular graphs, but okay. Because, okay, so the Hamming graph, the Johnson graph, the Grassmann graphs. The Grassmann graphs, in the Johnson graph, you look at sets. And you can think as a set as a vector space over a field with one element. So what you do instead of the sets, you look at the t-dimensional subspaces of n-dimensional space over a finite field, say CFQ. And then you join two of those spaces if their intersection is maximal, if the dimension of the intersection is t-1. And then you have the bilinear form graphs and the sesquilinear form graphs and the dual polar graphs and so on. But this, and certainly these are almost all the distance transitive graphs. I only look at the primitive ones. I will give a definition later. One way to look at distance graph is that they give a way to study these classical objects from a unified combinatorial viewpoint. There are four known infinite families with unbounded diameter of vertex transitive but not distance transitive distance regular graph. The Ustimenko graph, the Hamilton graph, the Doob graph, and the quadratic form graph, or the Egawa graphs. On this mode, there's only one infinite family known with unbounded diameter, which is not vertex transitive. That is the twisted Grassmann graphs, and this was discovered by Edwin Verdam and myself. And they have two orbits under their full automorphism group. So now I will look at the primitivity of a distance Rayleigh graph, because I would like to discuss primitive distance Rayleigh graphs. That can be a distance Rayleigh graph with intersection array k b1 up to bd minus 1, a1, c2 up to cd minus 1. And define the graph gamma I with vertex v gamma such that the vertices x, y are adjacent if in gamma y, if the distance in gamma is I, and that you can do for I is 1, 2, 3 up to d. Yeah, you can also do it for I is 0, but that is very boring. Yes, then you get a very boring graph. Yes, the graph is called in primitive if there exists an I at least 1, so the gamma I is not connected, and we call it primitive otherwise. So if all the gamma I's are connected, then it's primitive. And Smith showed that a distance Rayleigh graph with diameter at least 3 is imprimitive if and only it is bipartite. That means gamma 2 is not connected, or it is antipodal. That means gamma D is not connected. All the known primitive distance Rayleigh graphs with diameter at least 9 are the polygons in the families I mentioned before, or related to the Hamming or the Johnson graphs. You have the folded cube, the half cube, the folded half cube, and so on. And Bannai in the early 1970s, or late 1970s, I should say, of course, after Dasser's thesis, is to classify the primitive distance Rayleigh graphs with large diameter. He conjectured that we know all the intersection rates of the distance Rayleigh graph with large diameter. We don't have any counterexample yet. So note that the twisted Grassmann graphs are not counterexample to his conjecture. They have the same section array as the Grassmann. I will focus on a subproblem of Bannai's problem, namely when is a distance Rayleigh graph characterized by its intersection array. In the following, given distance Rayleigh graph with intersection array k b1 up to bd minus 1, 1 c2 cd, is this the only distance Rayleigh graph with this intersection? Of course, I mean up to isomorphism. And this is a difficult problem in general. I will discuss this for the rest of this course. This is the main topic of this course. So I will need the association matrix for gamma is the symmetric matrix A indexed by the vertices such that AXY is 1 if X is adjacent to Y and 0 otherwise. And we say the eigenvalues of gamma are just eigenvalues of A. Yes, yeah, there are maybe more adjacent matrices because the order of the vertices may give a different adjacent matrix, but they are all similar to each other. You only need a permutation to change the two matrices. And note that the eigenvalues of gamma are total real algebraic integers. That is an algebraic integer so that its minimal polynomial has only real roots. Sometimes important to know. And the reason why I mention it is if eta and theta are eigenvalues of gamma and algebraic conjugates, then their multiplicity must be the same. Now I will look at the distance of the eigenvalues of a distance Heilig graph. And so first I introduce the matrix L, and that looks like this three-diagonal matrix. It is 0, B0, 1, C1, A1, B1, C2, A2, B2, and so on. D plus 1 times D plus 1 matrix L. And this is an important matrix for us because if gamma is a distance Heilig graph, then theta is an eigenvalue of gamma if and only if theta is an eigenvalue of L of gamma. Note that the multiplicity of L gamma of any eigenvalue is 1, whereas the multiplicities of theta as an eigenvalue of gamma are usually much higher than 1. This implies that gamma has exactly d plus 1 distinct eigenvalue. And now I will introduce the standard sequence and the standard representation of a distance Heilig graph. So we have a distance Heilig graph with intersecting radius, and we have an eigenvalue theta of gamma. Then we can define a sequence ui from I is 0 to d by u0 is equal to 1. And that satisfies the recurrence relation ci times ui minus 1 plus ai times ui plus bi times ui plus 1 is equal to theta ui. And therefore I is 0 to d, where we assume that u minus 1 is equal to ud plus 1 is equal to 0, that these two numbers are just 0. The sequence ui called the standard sequence or cosine sequence for gamma corresponding to theta. I will give an explanation why we call it the cosine sequence later. The more standard notation is standard sequence, and sometimes important to notice that ui is a polynomial of degree I in theta. This is the reason why the graph is called P-polynomial, but I'm sure that Paul Terwilliger will talk about this later today. And now we look at the standard representation. So the fact is following. So we have a gamma distance Heilig graph with intersection as follows. And let theta be an eigenvalue of gamma with standard sequence ui. Then there exists a map sigma from the vertices to R to the Euclidean space of dimension m for some positive integer m, such that the inner product sigma x sigma y is u, the distance between x and y, and that's for all x and y in gamma. And you can take m to be equal to the multiplicity of theta because the rank of the vector spanned by sigma is exactly the multiplicity of theta. And we call the map sigma the standard representation of gamma with respect to theta. And the standard representation is the reason for the name cosine sequence, as the ui's all lie between 1 and minus 1. So we can think it as a cosine over an angle. So now I will talk about Big's formula.
I will not need it in this course really, but it's better to. So you can calculate the eigenvalues given the intersection rays and also the multiplicities given the intersection rays. So given the eigenvalue of a distance Rayleigh graph gamma, and we look at the UI is a vector with as entries the UIs. It is a d+1 length d+1 vector. Then it's not so difficult by the definition of the standard sequence that this is a right eigenvector of gamma for theta. So that shows that all the eigenvalues of L are eigenvalues of the distance Rayleigh graphs. The other direction I will not show. Maybe Terwilliger will show that. And you can now multiply the multiplicity of theta, and that is given by the following formula. I'm sorry, which is known as the Biggs formula. The multiplicity is V over the sum from I0 to D Ki times Ui squared, where V is the number of vertices. Ki is the order of gamma I of x. We fix in vertex x, and then Ki is gamma of I of x. But the Ki does not depend on x, because you can easily see that K0 is 1, K1 is K, and Ci times Ki is Bi minus 1 times Ki minus 1. And the sum of the Ki's must be equal to. Sometimes it's important to know that the multiplicity rational function in theta, and it's sometimes good to know when you try to solve things like the Bannai conjecture, you must know these sort of things. Another remark I want to make, the multiplicities are positive integers. And this is a very strong condition. In the theory of orthogonal polynomials, the multiplicities are called, that formula is called the Christoffel number in the theory of orthogonal polynomials. But I'm not going into that part of the. Okay, so this was, I introduced the distance Rayleigh graph for now, and I introduced, I give you examples, and I give you Bannai's problem. Now I will talk about characterizing some graphs. So we will use all those tools I introduced now. I will now look at the characterization of the Hamming and the Johnson graphs. And I will mainly talk about this Rayleigh graph with a quadrangle, with an induced quadrangle. And most of the section here in this and in this section are due to, most of it is due to him. So first we need to show an upper bound for the second last eigenvalue of a distance Rayleigh graph when it contains an induced quadrangle, and that is the following. Let gamma be a distance Rayleigh graph with intersection ray and this and with distinct eigenvalues k greater or equal to θ1 greater or equal ... to greater or equal to θd, because that's exactly d+1 distinct eigenvalues. So, and they are all real numbers, so I can order them. And if gamma contains an induced quadrangle, then θ1 cannot be more than b1 minus 1. Moreover, we have equality in this bound. Then the standard sequence with respect to θ1 satisfy ui minus 1 plus ui plus 1 is equal to 2 ui. And so we can give later on also a closed formula for ui's. That is what it means. And this will be very important. How do you prove this bound on the second last eigenvalue? And I will give another later on. I will generalize this proof to larger subgraphs of the distance of the distance Rayleigh graphs. Yes. So let ui be the standard sequence with respect to θ1. Let sigma be the standard representation with respect to θ1. And now consider the following inner product. We have the standard representation. So we look at the sigma x plus sigma y minus the sigma u minus sigma w with itself. Yes. So what we do is we take the two antipodes versus the two other antipodes. That is what really happens here. As an inner product, we must it must be at least 0, and this is equivalent with θ1 at most b1 minus 1. You can calculate this easily. I let the calculation. You can do the calculations. It's not so difficult. It's fairly easy. You have all the information you need for this. And moreover, it is if θ1 is equal to b1 minus 1, then p is 0. And that means that sigma x plus sigma y is the same factor as sigma u plus sigma w. So now we take a vertex x, set, so that the distance x and z is I minus 1, and the distance between y and z is I plus 1. This means that the distance between u and z and w and z is exactly I. And this holds for, and you can always find these vertex sets. So that's not so difficult to find just a vertex set. Assume that θ1 is b1 minus 1. So then we look at the following formula. We know that ui minus 1 plus ui plus 1 is the inner product with sigma z and sigma x plus sigma y. But we know because θ1 is b1 minus 1, we know that sigma u plus sigma phi is equal to sigma x plus sigma y. So therefore the inner product sigma z and sigma u plus sigma phi is exactly the same. But this we can calculate as 2 ui because the distance is exactly I. So that shows the formula I wanted. And this completes the proof. So now we assume that we gamma contains an induced quadrangle and that θ1 is b1 minus 1. Then the standard sequence ui with respect to θ1 satisfy ui is equal to 1 minus I times a1 plus 2 over k. And therefore I 0 to d. And the proof is fairly easy. It's just an induction with respect to I. And it's essentially all trivial, yes. So you know that u1 is θ1 over k, and that is what making a mistake. This would be b1 minus 1. Okay, I'm sorry. But that is equal to k minus a1 minus 1. That's b1 minus 1. And that is, you can easily see that is equal to minus a1 plus 2 over k. I'm sorry, I make here a mistake. And we continue the proof, and the proof is straightforward. Yes, not going to, you can read it yourself, I think. So this finishes the proof. Yes. So now I will follow BCN sections 314 and 315. BCN is a book by Brouwer, Cohen, Neumaier, and with the title Distance Regular Graphs, if you are not familiar with it, published in 1989. So root representation tau of a graph gamma is a map tau to a Euclidean space of dimension m for positive integer m, such that the inner product of tx minus ty, tau x minus tau y with itself is always even for all x and y vertices of gamma, and it is 2i for the distance at most 2. If the distance between x and y is I at most 2, then it should be exactly 2i. And in strict if the inner product is a most 4, if and only if the distance is most 2. And what is a root graph? Is a connected graph that has root representation, and a strict graph is a connected graph that has a strict root representation. The reason why it's called a root graph is that the representation that if you look at the vectors, the integral combination of the vectors of by the group, you given a root representation, you look at the x minus tau y for every x of y, and then you take an integral linear combination of these vectors. That gives you all lattice, and this lattice must always be a root lattice. And that is the reason for the name graph. Luckily for us, the root lattices are classified by Wheat in the 1940s. So we know all of the root lattices. And it's not so difficult to see the following lemma. I'm not going to prove it. It is in this one of these two sections, 314 or 315 of BCN. A connected graph with small eigen minus 2 is always a root graph, and a regular root graph of diameter most 2 has always eigenvalue at least minus 2. So it is a generalization of graphs with small eigenvalue at least minus. Okay, we have quite a few examples of root graphs. So we have the Hamming graphs, the Johnson graphs, the loop graphs, the half cubes. What are the half cubes? You take the distance 2 graph of an hypercube, and this has 2 components because hypercube is bipartite. And you take one of the 2 components. That is a distance regular graph, and that is we call that graph the half cube. And the icosahedric, and also the Gosset graph, and so forth. So now I will talk about amply regular graphs. An amply regular graph with parameters NKAC. A graph is called amply regular with parameters NKAC. If it has n vertices, is regular with VCK. That means every vertex has k neighbors. Any 2 adjacent vertices have exactly a common neighbors, and any 2 vertices at distance 2 have exactly c common neighbors. And distance regular graphs are clearly an example of amply regular graphs, but there are many other graphs that are amply regular. Amply regular graphs are much wider concept than distance regular graph. So Neumaier has classified the amply regular root graphs with C at least 3. You can see, for example, theorem 3.15.1. In BCN, in that theorem 3.15.1, they claim a more general result. They claim that they can classify all the graphs with having constant C, and K regular graphs with have a constant C. But that is not true, because with Brouwer we found a new infinite series of regular uniform geodesic graphs in I think that was long time ago, let's say so. And that there exists another graph with C is equal to 4, and that graph is not amply regular. So what do I need to say? In principle, theorem 3.15.1 can be repaired, but you have to add this new family. And if you look at the additions of BCN, you can find them on the internet. You can see for a simplification and correct proof of that theorem. Now you look at the non-complete amply regular root graph with parameters C at least 3, and then you have only these examples: a cocktail party graph, C is 10 and gamma is the Gosset graph, the Schlafly graph, and half a cube for C is 6, and a Johnson graph or a Chang graph. There are 3 Chang graphs. They have all the parameters as Johnson 8, 2. But that is only a case where Johnson graph is not determined by its intersection array. And I will show this later, don't worry. But exactly, this shows it already. Yeah. For CS2, you need you have to use the strict root graph condition. It is not true if you remove the strict part. So now we can look at the non-complete amply regular strict root graph with parameter C is 2. I don't know. Then either it is gamma Hamming graph, or if A is 2, then gamma is a Cartesian product of 4 cliques, strict-handed graph, and the icosahedra. I already said that it's not true if we remove the strict root graph condition. With Brouwer and Andries Brouwer and Misha Klin, we found a counterexample. That's a paper that is also quite old, I think 2001 or 2002. Now we come back to this graph with an induced quadrangle having second eigenvalue. The second last eigenvalue, θ1, is equal to b1 minus 1. I'm sorry, I've missed here the word quadrangle. We show that such a graph, this graph is strict root graph. Let sigma be the standard representation with respect to θ1, and that is b1 minus 1. Then you have this inner product. Yes, sigma x minus sigma y with itself is 2u0 minus 2u dxy. That is because u dxy is 1 minus, what was it? A plus 2 over k. Did I make here a mistake? Maybe I make here a mistake. Maybe it should be a1 plus 2 over k, but it doesn't really matter. If I make here a mistake, I'm sorry. It should be a1 plus 2 over k, then it does not really matter for my proof. But so if you now multiply this representation with the square root of k over a1 plus 1, and if this is not the right number, then a1 plus 2, then that is a strict root representation. So then we see that we have the classification as done by Terwilliger in the late 1980s, 1986 or so. He showed this theorem. So it shows that if you have an induced quadrangle and you have θ1 is equal to b1 minus 1, you have only one of those following graphs. Yes, that is quite amazing. Note that I assume D is at least 3. For D is 2, you get several more examples, but they have all even C2. But for C2 is 8, you get the Cleverly graph, for example. And for C4, you get, for example, the Chang. Shows that the Johnson graphs and Hamming graphs are usually characterized by their intersection array. I think this is where I'm going to stop today. I think my time is almost over. So thank you for your attention. I will continue tomorrow.
Any questions, anybody? Questions, anybody?
How much different, Jack, is this proof from the one in the text? Are there substantial shortcuts, or are you just summarizing what's already in BCN?
Everything is, I should summarize essentially what is in BCN. So I give a sketch of the proof, and you can, there's not really shortcuts really possible. I think if you use only this Rayleigh graph, the proof can be shorter.
Thank you.